Hello, and welcome back to STEM Online Academy. My name is Jason Masterakos. Okay, so today, as I promised from last week, we're going to do a problem solving tutorial today, and it's going to be specifically on projectile motion. Um, it's a really interesting problem on orthogonal impacts. Okay, so the slope condition that most of you guys will miss. Okay, so let's look at the problem here, right? So you can see that I've drawn a, projectile type of motion starting from the origin at 0, 0, right? And the projectile goes in a two-dimensional space, okay? So uh, the first thing is that most students will solve the projectile motion by asking just one question, okay? Where does it hit, right? So the projectile, right, obviously goes in a parabolic motion because of gravity, and it hits some target, okay? That's the point of it. Okay? But this problem asks something that's actually much harder, okay? Can this projectile, right here, right? Can this projectile hit the target line at exactly one right angle? Okay, so can this projectile hit this right angle here at point P? Okay, so it needs to be orthogonal. The projectile has to hit it orthogonally. Okay, all right. So because now the intersection is not going to be enough, right? The projectile just must hit the line, right? The projectile must hit the line, right? But it must also hit it orthogonally, as I mentioned. And that means that the real hidden concept here is not just projectile motion, okay? It's a mixture of using calculus and geometry, right? As you can see here, geometrically, I've drawn the projectile. And since our projectile, right, is, modeled with V0, speed V0, and angle theta, right? Its trajectory equation is given by this guy right here. If you haven't seen a trajectory equation before, that's not a problem, okay? So y projectile is equal to all of this, right? That's our problem. And we just want to determine all theta that is between 0 and pi over 2, such that the projectile intersects it orthogonally, right? As I mentioned earlier, okay? But that means that the real hidden thing, as I mentioned, is not just the projectile motion, right? It's mainly calculus and analytic geometry, which is what we're going to do. And this is exactly the kind of problem where a lot of students will know the formulas, but they will freeze on the exam because this type of problem is not something that you would see often, right? Okay. Here, it's not a matter of knowing what formula to use. It's about rigorous problem solving. Okay. So let's get to it, right? Right. So I'm going to explain this verbally as opposed to doing the algebra as much. So I don't want to bore you. If I did all the algebra right on the board, you're going to die of boredom. So I think the best way to, for certain types of problems in math and advanced physics, is to explain it to you guys, right? Explain and get to the point of what I'm going to be solving for you, right? The problem that I want to solve for you, the client or the viewer, right? So today we're just going to break it down using my system. You know my system. I've talked about it in my other videos, right? And that is, right? Let's go to another page here. If you remember my system, for those of you who don't know, it's this. So here's my system. So here is the system that I use to solving any mathematical problem, right? And that is, we're going to do one, we're going to visualize, right? Visualize the problem, okay? So start off with visualizing the problem. Then we're going to model it. Okay, so we're going to model the problem. Okay, so model. Then from model, we're going to go to executing. Okay. Execute. And then we're going to verify. This step-by-step approach, since it's step-by-step, as long as it's done properly, we shouldn't miss any details. Okay. So using that framework, we're going to solve the following problem. Okay. So let's do that, right? So the situation, the projectile is launched from the origin, as I mentioned, right? From the origin with a fixed initial speed v0, okay, and an angle, a launch angle theta. It follows a parabolic trajectory, as you can see here. The target is a slanted line, right, sitting above the origin, right, as you can see, right here, okay. And we want to know which launch angle makes the projectile hit the line perpendicularly, right? So perpendicularly here. What's launch angle is going to help us hit hit the line perpendicularly? And not just hit the line, I mean hit it at exactly a right angle. It has to be exactly the right angle. If not, we haven't achieved our objective. Okay. And yes, this is tricky. Okay, this is a hard problem. Okay. I'm not gonna sugarcoat. So this is our problem. Okay. Now let's get to the point where you guys are struggling. You're struggling um where most people will struggle with this actually. You will immediately set up the projectile equation to equal the line equation. Okay, not to say that that's wrong, right? You're actually onto something. That's true, right? But that's not enough. Okay, yeah. Uh, we're going to say that y line equals y projectile. The equation of the line equals y projectile because the projectile's trajectory intersects the line, the equation of the line. So we have to set the equations equal. Sure, right? But that only answers where do they meet. Okay? This part here only answers where the trajectory and the line meets. Okay, it doesn't answer how they meet. So what you can see here, from what you can gather, the implication of what I'm saying is, when it comes to doing regular algorithmic problems, it's just formulaic. But when it comes to doing problem solving, the better you understand the semantics of the problem, you'll be able to solve the problem. Okay? It's not enough to use the formulas. You have to understand asking the right questions and the semantics of understanding it, the whole problem comprehensively. Then you can solve it, right? Otherwise, you'll just go in circles, and it'll be way. That's why it's way too hard for most people to solve these types of problems because they're not asking the right questions. Okay, so we want to ask, where do they meet? Oh, sorry, how do they meet? Right. This expression will only tell us where they meet. Okay, that's not good enough. And this problem cares about how they meet, not where they meet, right? How does the trajectory, right? The trajectory of this yellow path here, how does this trajectory intersect the line, the white line here? And that makes an um, orthogonal projection. Okay. This is the perception gap that everyone has. Okay. This is the major perception gap. Okay. And it's completely fine, but as long as we correct it, right? A normal projectile problem asks for position. This problem asks for position plus direction. So the student who only solves the intersection part has only half the problem. Okay. And that's not good enough. The missing half is going to be the slope. Right? All right. So now let me mention my personal connection to this. If you saw my last video, I was talking about two teachers that I had who were outstanding slash brilliant at finally getting me to understand how to do math problems, right, in high school. Okay. And then from there, I just excelled into university. I used to get stuck on problems like this too, not because I couldn't compute, right? Like the calculation is not the issue, right? Calculation was not an issue, and following the examples wasn't. But when the exam changed, actually, for me, anyways, the wording. Uh, when they changed the wording, I didn't know what to do first. Okay, that was sometimes a bit tricky. And quite often, teachers or professors will do that. They will change multiple variables to really mess you up, right? So we need to have a system that helps us be almost, what's the word I'm looking for? Fluid when it comes to tackling any type of problem. And it's not easy, though. I'm not saying it's easy, but there is a way to tackle a problem from different angles, if that makes sense. Okay. And what changed everything for me uh, was learning that these types of hard problems can be broken down into a geometric type of system. Okay. And that's why I teach this type of system when I do any type of problem like this, right? You want to visualize the phenomenon of what is happening. Okay. Right, so try to visualize what's happening. Okay. Then you go to modeling it. What I mean by model is take what you visualize from the phenomenon that you're dealing with, right? You model it, so you draw it, or you use, I don't know, you can use a simulation if you want, computer simulation, doesn't matter. But as long as that simulation or drawing is consistent with what you visualize, and you assign variables and quantities uh, that make sense, then you should be fine. You're on the right track. And then from the model, you want to execute, right? So what I mean is you take the model and you transform it into an equation that mathematically represents the model, whether it's a physical system or a geometric system. Doesn't matter what it is. Okay. And then from there, you use the mathematical techniques to verify. The verifying part is easier. The setting up part of the problem of any problem is always difficult. Okay. So let us apply that system. Let's apply my four-step system. Okay. All right. So step one, I want to visualize the problem. Okay. So first, we visualize the picture. Okay. I've already drawn it, as you can see. Okay. So here's the projectile. Okay. And you'll notice that we have a parabola that's rising and falling, for obvious reasons. Any two-dimensional projectile has the influence of gravity that pulls it down. That's why it's in that shape. Okay. Now, at the impact point, I will zoom in on my drawing here. My impact point, I called it point P. You can call it whatever you want. I'm calling it point P. Okay. So at the impact point, the projectile curve and the line meet. Okay. But because the impact is completely orthogonal, okay, so the impact is completely orthogonal, the projectile is not just touching or crossing randomly. You understand? It's not just touching. The projectile's direction, right, at that instant is perpendicular to the target. Okay, so the projectile's direction is completely perpendicular to the target line. That makes sense. Okay. So this picture actually has two important pieces, right? That the projectile, right, must pass through a point on the line. Okay, so projectile must go through a point on the line, a specific point on the line. But then the tangent direction, you should know what a tangent is. It means a line that touches a curve, any curve or circle at exactly one point, right? So that tangent direction of the projectile at that point must be at a right angle to the line. That's why I made this, you know, perpendicular projection. That red line here is the perpendicular projection of the yellow pathway, yellow trajectory here, where the yellow trajectory meets the line, right? Y equals mx plus b, right? Those two curves intersect at a perpendicular 90-degree angle. Okay, so the picture has those two important pieces. Okay, one, the projectile must pass through a point on the line, and the tangent direction of that projectile at that point must be at a right angle to the line, right? I hope you are following, right? I'm breaking this down using my four-step method, my four-step method here. Okay. Now, let's look at step two is modeling. So now we need to model this problem. Okay. What do I mean by that? There's going to be two conditions, right? So the first condition is that the projectile must be on the line. Let's go on to page two, right? I'm getting right to the point here, right? I'm just taking the equation of the line, right? So I call it y line, okay? So y subscript line, and that is equal to y subscript projectile, because since both the line and the projectile intersect each other, the projectile being the trajectory, right? Since those two curves intersect, their equations have to intersect, which means they have to set them equal. Okay. So the projectile must be on the target line, right? That is the intersection condition. That is part, this is one here that I've put, right? By projectile. Second condition is that the slope of the projectile at impact, right? Slope of the projectile at impact must be perpendicular to the slope of the target line. You see here? So slope, right? Slope of the projectile at impact must be perpendicular to the slope of the target line. And we know exactly what that expression is. When you have anything to do that is orthogonal to some curve, right? Some sort of orthogonality condition, you take the product of both slopes, slope of line, slope of projectile. Okay? Orthogonality condition. Now that's key, because if the target line has a positive slope, then the projectile must hit with a negative reciprocal slope. Okay? Oh, that makes sense, right? Okay, so again, I'm going to repeat myself. So if that's the case, right, this is key. If the target line has a positive slope, then the projectile must hit with a negative reciprocal slope. And that is the calculus slash geometry hidden inside of the physics. Okay. So the entire problem, right? The entire problem becomes more simple. It becomes finding the launch angle, right? What I mean launch angle. Hope you understand what I'm doing here. I've made a visualization by drawing this, and I've made some sort of a schematic model of what is the most important things that will help you conceptually understand how to do problems like this. I hope this helps. Like, you can always put something down in the YouTube chat. I always like comments in this video. Okay. So the entire problem comes finding the launch angle, right back here, angle theta, right? That little angle there. So find the launch angle that satisfies both conditions at points, but not separate. Both conditions at the same point, right? Okay. And that is why the problem is harder than your normal projectile motion problems. Okay. So we've got that. Step 3, we want to execute. We want to execute what we're going to do here. Okay. So step 3 is we're going to execute. Okay. Right. If you look back at my systems technique, we did visualize part 1. Right. We did part 1, step 1, step 2, model. Now we're going to execute. Execute. Okay. So now when it comes to executing, okay, we first take the trajectory of the projectile. Right. I'm going to take the trajectory of the projectile. Then we will find the slope. Right. Right. So then we're going to find the slope. And this slope will tell us the direction the projectile is moving at each horizontal position. Again, this slope is going to tell us the direction the projectile is moving at each horizontal position. Okay, has to. Because at the impact point, we're going to force the slope to be perpendicular to the tangent line. That's why condition 2, I wrote down condition 2 here as being very important. Okay, right, so we're going to force the slope to be perpendicular. All you have to do is use this second property. Right? And that gives us the horizontal location of the impact, right? In terms of the launch angle. Okay. Hope that makes sense, right? And even now you can try to visualize it here. Okay. Right. So I hope that is sinking in mathematically. Okay. Then from here, right, we're going to use the second condition. That same impact point, point P, I've called it, right? The impact point between the trajectory and the line, okay, that same impact point, right? We must also lie on the line, okay? Otherwise, it doesn't make sense. It won't be any intersection. So we need to substitute the impact location into the intersection condition, right? So substitute the impact location into the intersection condition. By the way, I've given you hints. You can actually algebraically do this yourself. And if you don't understand anything, you always rewatch the video. But I've given you a modeling schematic, the most important equations that you need to set up. But I'm going to let you do the algebra, right? Because I think that will be a good exercise for you to try it. If you have any questions, you can always ask in the YouTube chat. Okay. Now, you'll notice that, so we're going to substitute the impact location into the intersection condition. And then at this point, the entire physics problem collapses into an equation involving only the launch angle. Everything will be as a function of theta. And that's a major breakthrough because the question is asking us to solve for theta. So if we have it only as a function of theta, we can use mathematical techniques to do that. We started with a projectile. We started with a line, a trajectory, an impact point, and a slope condition. But the system's just reduced, right? The system completely reduced everything to just the angle. Right? The equation is just dependent on the angle, no other variable. And that is what good mathematical modeling is reducing it down to its most descriptive points, right? To its most descriptive variable, I should say. Okay, and that's going to remove any confusion that you have, right? So you can see there's a difference from visualizing, right? So this is the visualizations drawing I've made of the trajectory, and then for the model, you just want to make the most important to the point equations, little equations. They don't have to be big, and you don't have to algebraically do it. But they're almost like frameworks. I like to call them framework equations. So that's why you can do the rest of the algebra, right? It's about setting up the framework equations. If you set up the framework equations, then you're done. That's all it takes for problem solving in math. Okay. All right. So let's look at the main result now. Okay. So here's the important conclusion. Okay. There's not always a valid launch angle. Okay. As you can see, the angle here, it's always a valid launch angle. But the projectile must have enough speed, right, relative to the height of the target line. Okay. Because if the launch speed is too small compared to the height of the line, right? When I mean height of the line, I'm talking about this, right? Right? Because think about it, if the launch speed is too small, compared with the height of the line above the origin, right? Because this white line is above the origin. Okay, if you were to, let's say we had some perpendicular height here above the origin, that dashed line that I've made. Okay. As I said, if the launch speed is too small compared to the height of the line above the origin, then there is no launch angle, right, that can be produced to require that perpendicular or orthogonal impact. Does that make sense? Otherwise, this wouldn't be a projectile. The problem will just collapse. This won't make any sense. Okay. However, if the launch speed is large enough, then the model gives exactly one physical valid angle in the first quadrant. When I mean first quadrant, I mean this. I haven't drawn all the quadrants. We don't need to put all 4 quadrants. This is just a projectile motion that's positive, right? And that means that the answer is not try any angle, right? And it also isn't there are always 2 projectile angles. No, those would be wrong. Right? Okay, so let's move on to the next part here. And that is why this is actually a good problem, why it will come up on a exam, mainly out of anything. It will probably come up on an exam mainly. This is why the problem is so good. Right? It's going to combine 3 things that a lot of students often study separately. Okay, because there's multiple concepts involved here. One is projectile motion, as you can see here in the drawing, right? So it involves, mechanics. Okay. Another one is the derivative of the slope. I mean, the derivative as slope, because the first derivative is the slope. Sorry. Okay. That's a calculus concept. Okay. Right. So you probably won't see this in your very first physics class. You'll see it in a calculus-based physics class because it requires you to know about slopes. Okay. And perpendicular lines. So it requires geometry, calculus, and mechanics. Okay. So most students know each of these ingredients. They've learned in the classes. But the exam difficulty, why it's difficult, is because it comes from combining them in the right order, right? And this is why my system matters. You want to visualize, right? You want to visualize the projectile, okay? You want to visualize the projectile as it hits the line at the right angle again and again. I keep emphasizing the visualization, okay? Projectile hits the line at the right angle. Then you want to model. The model is setting up framework equations from the visualization, okay? These guys here. When I mean frameworks, this gives you an idea of how to set up your equations and what you need to solve. Okay. All right, so we're at the model intersection plus perpendicular slope. Okay. That's also part of this. This is part of step 3. Forgot that, right? So not just orthogonality condition. Finally, you want to, for your model, you want to put the intersection plus the perpendicular slope. Okay. Section plus, so that's perpendicular slope plus the intersection equations, the y line minus y projectile, because as you can see in step 1, y line equals y projectile. But if I rearrange it by subtracting both sides, then I get an equation I can add them. I can't just add it like this, right? The y line equals y projectile plus the orthogonality condition, because the intersection point is perpendicular tangent from the trajectory to the line, right? So I hope that is making more sense, right? Okay. And finally, once you have that equation in step 3, you want to execute. And the execution process means you're going to differentiate. You're going to combine the two conditions and then solve for the launch angle. So by differentiating, right? So differentiate, combine both conditions, and then solve for theta. How do you solve for theta, you're asking? It depends the type of equation that is produced out of it. Okay? Again, you could ask me in the YouTube chat once I've uploaded this video. Yep. And then finally, you want to verify, right? So check that the angle is physically meaningful, if it physically makes sense, right? For instance, as I mentioned earlier, if my trajectory is going, is not high enough, if it goes not above the launch angle, then I can never reach having the orthogonal impact point, right? So if I'm getting a negative angle, that will really tell you something is off, actually, because that won't even be in the first quadrant. There won't be any trajectory whatsoever going upwards. So make sure that your angle physically makes sense, okay? Right? That's what we've got there. And then finally, for step 4, we want to verify, right? And verify means now we verify the answer. We have a valid solution that must pass the 3 checks that I mentioned earlier, right? 3 checks here for my system, okay? Valid solution must pass those 3 checks: visualize, model, and execute. This is really handy for physics problems, by the way, okay? So first, the angle must be between the horizontal and the vertical launch, right? See how much I'm referring back to the drawings as opposed to the equations. The drawings is more important, actually, okay? So again, right? So must follow the 3 checks. First, the angle must be between the horizontal and vertical launch, as you can see. Second, the impact point must actually lie on the target line. Impact point P launches right on the target line. Okay. Third, the projectile, right? The projectile slope, right? The projectile slope, as you can see here. You can figure out what I mean by that. Projectile slope at the impact point must be perpendicular to the target line. The perpendicularity is the red line that I've made. I could have made a red dash line, but the red dash line there, which is perpendicular to the line y equals mx plus b, which is intersecting the trajectory, the yellow trajectory curve. Okay. If any of these fail, right, the answer is not going to be valid. Okay. Yes, that's annoying how physics works, but if one little thing is off, the whole thing is off. Okay. This is the step that most of you guys will miss, but I hope this is helping you understand it better. This will solve any equation, right? And it will assume, right? Well, this approach, if again, I have to emphasize, this approach will solve any problem if it's used correctly. Now, it's not 100% because sometimes the problems are too hard, but it gives you a very good framework on how to start the problem. Okay. So I want you to think about that, right? I want you to think about how you can use this to solve your own problems. Okay. So in the step 4, right? Let's see. See, on harder exam problems, right? Solving is not the same as verifying, right? So when you solve a problem, go back, try to verify it, try to see if anything is working, right? Quite often people rust on exams and it becomes a problem. Okay. Final answer must satisfy some sort of geometric approach here, right? Otherwise, something's wrong. Right? That's why the last step of my system is always you need to verify. You have to verify all the time, right? I don't care if the exam is really hard and you're pressed for time, you need to go back to your problem and verify. Okay? Always verify. So if this problem felt difficult, that does not mean that you're bad at physics or, you know, anything else for that matter. It means the problem hid the real condition, right? Problems like these hide a lot of constraints, um, a lot of important parameters that you need to be able to extract. It's not always easy to do it. Trust me, myself, I have trouble sometimes when I look at a very hard problem. It's just trying to relate with you guys. It's the same thing, right? But I try to use that approach, right? It means that the problem has a hidden condition, right? Now, most of you guys look for where the projectile hits, but the problem asks how it hits, not where it hits, but how it hits. How it hits is more important than just using framework 1, y line equals y projectile. Still correct, but you need to know how it hits, how the trajectory is hitting the line. Okay. And that is a different question entirely. Once you see that, the problem becomes much less mysterious. And the hidden key is the intersection tells you the location, right? That's all it tells you. The slope tells you the direction, and the orthogonal impact requires both, right? That's the whole thing to the problem, right? And that is it. Okay. So let me summarize, right? The main mistake is solving only for the intersection, right? If you only solve for the intersection, if you only did y line equals y projectile for your framework, then you're doing something wrong. Okay. But orthogonal impact requires the projectile to meet at the line at the right angle. So the correct setup has two conditions. The projectile must hit the line, and the slope of the projectile at impact must be perpendicular to the slope of the line. Okay. So when those two conditions are combined, the problem reduces to one launch angle condition. And if the launch speed is large enough relative to the target height, then there is a physically valid launch angle. If not, there is no launch angle. That is the complete solution. That's it for today. If you understood this lesson in class, but freeze when you have an exam, when there's a change in setup, when there's a hard problem. This is exactly what I help students fix. I teach hard. I teach hard calculus and calculus-based physics problems, right? Using my visualize, model, execute, and verify systems technique. This is the same system that helped me go from struggling in mathematics to earning a double degree in mathematics and physics with a 3.9 GPA out of 4. Okay. So if you're preparing for a hard midterm or final and want help learning this method, there'll be my coaching services will be in the link below. Comment impact if you want more calculus-based physics problems like this. Okay? Don't forget to like and subscribe. It is always a pleasure. Bye for now, guys.